I want that one. How's it going, everyone? So this is Volcanoes Lab 1 or Lab 5 overall. And I will jump right into it. So this lab's going to look at volcanoes and kind of just an intro to them and some basic ways of how to predict when more eruptions will occur and different hazards associated with volcanoes. And we'll be looking at the Augustin volcano in southern Alaska. So the first part of the lab is going to be calculating repose times. So that is the difference in time between when one eruption occurred to the next eruption. So it's not too bad to calculate. We just take the difference in time. So this first example here, you would just take 1883 minus 1812. That's a 71-year gap. So we could do that for all of them. And then from there, we can find an average repose time. And then it gets a little confusing in the middle because we have one that lists 1963 and 64. I would just list two different years. So I would take 1964 minus 1935 and also 1963 minus 1935. And that'll give you 2 years. And same thing with 1976. You could take 76 minus 64 and 76 minus 63. And that's all right. You can just list them like that. But then it'll ask for the average repose time, which would be adding up all of the repose times divided by, I would count this as 7 eruptions. And that might get a little confusing with the multiple listed ones. I would just kind of use the number in between. So if you found maybe a year that was 13/12 years, you could just use 12.5 in this calculation. It should be close enough. And so this is a kind of a nice first step of trying to calculate when the next eruption will occur. So we said, well, on average, it erupts every so years. It's not perfect. And then we'll even see with this spread of numbers, they can be pretty different. So it might be better to use a range and say, I believe 71 was the biggest gap. So maybe it erupts between like 10 to 71 years or whatever the low number is you find. But even that like isn't a guarantee. The Earth likes to do its own thing. But it's a good start. It's a good start of how to predict volcanic eruptions. So one of the hazards with volcanic eruptions is pyroclastic flow deposits. And these are very, very dangerous. They're made up of different volcanic matter and gases and different rocks that get blown out from the volcano and then kind of roll down the surface of it. And they can cause a lot of damage. So we've given you two different images here of the Augustin volcano. So the black and white one is just your standard air photo, and then this colored one is a false color image. It makes the vegetation red just to make it easier to see the contrast. And we ask a few different things of you. So on this black and white image we give you, you're going to have to draw a few things and submit that. We want the outlines for the 1963-64 volcano, pyroclastic flow deposits, and then also the pyroclastic flow deposits for the 76 outline. And that's not too bad. We can kind of see the difference in color here, like this lighter color versus this is probably vegetation, and it's really easy to see on the 76. So I drew just a quick little outline to kind of give an idea what we're looking for. And then you're going to put that on this one, wherever that falls. And it doesn't have to be perfect. You don't need to worry about every little bump, just kind of get an average throughout. And then we also want one that's roughly double the outline size. So it's going to be out here somewhere, kind of off the page a little bit, and that's all right. So kind of saying it's a even more dangerous eruption. What should we be preparing for? And then we also want some X's where the pyroclastic flow material enters the ocean. So the ocean's over here, and we can kind of see there's an opening here. So this is probably just an open kind of slope. The material can reach the ocean, and we can just see the color stays the same. So that's where the material entered the ocean, these last eruptions. And then I think one question asks about Burr Point. I just circled it here so you know where it is. Okay, so the next part is looking at tsunami predictions. So let me just explain this image for a bit and what's going on. So this is the Augustin volcano that we're looking at, and here's the Homer Spit. The Homer Spit looks like this. It's really low to the ground, and it is at a kind of a high risk for tsunamis. So if you imagine a tsunami kind of comes through here, it can do a lot of damage. So because of that, it's really important to have predictions in place so that we know when it's going to occur, so we can give proper warnings and people can evacuate. Okay, so we drew a line between the volcano to the Homer Spit, and we split it up into different segments. And so the reason we did that is it's based off of depth, because tsunamis are going to move differently depending on water depth. So we split it up to try to be a little more accurate on time, and I'll get into that. But on the side here, we kind of give the water depth of that segment and how far across that segment is. So questions 8 through 10 just ask for the length across. So no tricks, we just give them to you because it's kind of hard to measure on screens. So segment 1 is just 18.3, segment 2 is 45.5, and so on. And then keep in mind that segment 1 is 30 meters depth, segment 2 is 70 meters. We're in the middle there, it's getting deeper, and then segment 3 is back to 30 meters. So in order to first get a time, we need a velocity to figure out how fast the waves are going. So we can find a velocity by taking the square root of depth times gravity. But we're going to need to convert to get in units that we can use. So by using that depth times gravity equation, we get it in meters per second, but to be useful, we're going to need it in kilometers per minute. And because, as I pointed out here, we're dealing with two different depths. We're dealing with 70 meters versus 30 meters. That's going to be, the velocity will be different depending on that depth. So we have to do two different calculations, one for 30 and one for 70. And so we can do that calculation, and then we can convert meters divided by meters per second to meters per minute by multiplying by 60. And then from there, we can get it into kilometers per minute by dividing that answer by 1,000. And doing that will get us question 11 and 12. And then from there, we can try to get to time. So time is going to be distance divided by velocity. So distance was given in that first image here, these distance of the segments. So the idea is we can find the time for each segment and then add them together. So segment 1, we could just take that distance of 18.3 and divide it by the velocity we found for the shallow water, the shelf. And then for segment 2, same deal, we could take 45.5 divided by the velocity we found for the deep water shelf, because this one's at 70. And then segment 3, 46.8 divided by the velocity we found for the 30, the shallow one again. And then once we have those three, we can add them together, segments 1 through 3, to figure out roughly how long it will take a tsunami that started here to get to the Homer Spit. All right, so the next part is going to look at ash hazards. So ash is pretty dangerous and can cause a lot of issues. Can cause issues to people, of course, lots of health issues, issues to planes, issues to crops. It can be pretty dangerous. So the next part's asking to draw a circle around all of the affected cities of this Augustan volcano. So we list a bunch of cities, and then on this image, you're just going to want to draw a big circle encapsulating all of them. And then it gives a little description on this wind direction chart. So think of it kind of like it's pointing. So the little points here are pointing to the direction of the wind. So this arrow is kind of showing that direction. So they stay pretty constant between winter, spring, summer, fall. Maybe a little variation, but all mostly going northeast. So the next part is going to look at volcanic ash hazards with airplanes. So these two images are showing ash underneath a microscope. And then you don't need to really worry what polarized versus plain light means. That's just something geologists use to help identify minerals using like color. And so one of the questions is going to ask what material is in the volcanic ash, and you can just list the words that it gives here. It already points them out for you. So no tricks there. And then there's two main hazards to be careful of with volcanic ash and plains, and that is abrasion and melting. Abrasion, things like scratching. So the lab mentioned something called the Mohs hardness scale, which looks something like this. It puts all rocks on just a list of hardness based off of from 1 to 10, 1 being the softest, 10 being really, really hard. And things like fingernail, copper coin, knife, steel, that means it can scratch. So a fingernail can scratch anything lighter than a 3, a copper coin can scratch anything lighter than a 4, so on. So to give an idea, airplanes are often made of aluminum because it tends to be pretty light, but that aluminum only has a hardness of 2 to 3. So it's up here and it's pretty soft, like a copper coin could scratch it. And then we have a list of all these different minerals that we found in ash, and they all have hardnesses of 5 through 7. So they all can scratch aluminum. And then plexiglass windows, also part of airplanes, a little harder, 3 to 4, but still softer than all the minerals in ash. So if a plane was to fly through an ash cloud, it would get scratched up pretty bad, which can be pretty dangerous. And then the other risk to flying within an ash cloud is the melting point. So the ash is already pretty hot, but airplane engines reach a temperature of 1,400 degrees. So even if we have some minerals that are in the solid form, certain ones will melt. And so we don't really want molten rock in an engine. It can shut it off and cause serious damage. So I'll give an example for hornblende, for instance. Hornblende has a melting point of 840 degrees. So anything below 1,400 is going to melt, right? So hornblende is definitely within that realm. It's going to melt pretty easily, and it's going to stick to the inside of engines. And these minerals have been known to like completely shut down airplanes in the air, and that's not ideal. And then I think one of the last questions is talking about sandstorms and why is it not as risky to fly through a sandstorm versus an ash cloud. And so I'll let you know that sand is mostly made of quartz. And so quartz is still pretty hard. It can still scratch up an airplane. You probably don't want to do it. But we do notice that this melting point is above that 1,400 degrees. So it's not hot enough to melt quartz. So I'd keep that in mind. It probably won't be as dangerous because it just can't, an airplane engine just can't melt it the same way it can these other minerals. And yeah, that's all I have for you. So let me know if you have any questions.